My dear students, welcome back to our channel. In this video, I will be explaining the B.Sc first semester subject Chemistry as prescribed by Osmania University and other universities of Telangana. We will go through the important questions and answers one by one. Let's begin with a quick revision. Unit 2 first important short question is: define inductive effect and explain the factors influencing bond polarization. Inductive effect and factors influencing bond polarization. The inductive effect, I effect, is a permanent effect in organic molecules. It occurs due to the unequal sharing of electrons in a covalent bond because of difference in electronegativity between atoms. This causes bond polarization, creating a partial positive and partial negative charge. For example, in chlorothane, CH-CH-Cl, chlorine is more electronegative than carbon, so it pulls electrons towards itself. As a result, Cl becomes and the carbon atom becomes. This effect is transmitted through sigma bonds but decreases with distance. Factors influencing bond polarization. 1. Electronegativity, greater the difference, stronger the inductive effect. Example, FCl-Bri. 2. Nature of substituent. Electron withdrawing groups, I, NO, CN, Cl. Electron releasing groups, I, alkyl groups like CH. 3. Distance, inductive effect decreases rapidly with distance from the substituent. Easy memory tip. I effect pull or push of electrons through bonds. Thus, inductive effect helps us understand reactivity, acidity and stability of organic molecules easily. Next important short question is: 2. Explain resonance, mesomeric, effect with a suitable example. Resonance, mesomeric, effect. The resonance effect, also called the mesomeric effect, M effect, is a permanent electronic effect in which ELECTRONs or lone pair electrons are delocalized over two or more atoms in a molecule. Because of this, the actual structure of the molecule is not a single structure, but a resonance hybrid of all possible contributing structures. A common example is benzene, CH. In benzene, the double bonds are not fixed. Instead, the ELECTRONs are spread equally over the entire ring. This delocalization makes benzene more stable than expected. Resonance effect can be of two types. M effect, electron donating groups like OH, NH donate electrons by resonance. M effect, electron withdrawing groups like NO, CN pull electrons by resonance. For example, in phenol, the OH group shows M effect, increasing electron density in the ring. Easy memory tip. Resonance sharing electrons over many atoms. Resonance explains stability, reactivity and orientation in organic reactions. Next important short question is: 3. What is hyperconjugation? Explain its role in the stability of alkenes. Hyperconjugation and stability of alkenes. Hyperconjugation is an electronic effect in organic chemistry in which sigma electrons of a C-H bond interact with an adjacent bond or empty p orbital. It is often called no-bond resonance because the C-H bond seems to disappear in resonance structures. In alkenes, hyperconjugation occurs between the C-H bonds of alkyl groups attached to the double bond and the ELECTRONs of C-C. More alkyl groups mean more C-H bonds, so more hyperconjugation takes place. For example, compare these alkenes. Ethene propene, but2ene. Ethene has no alkyl groups, so no hyperconjugation. Propene has one alkyl group, while but2ene has two. Therefore, but2ene is the most stable. Hyperconjugation spreads electron density, reducing energy and increasing stability. Easy memory tip. More alkyl groups, more hyperconjugation, more stability. Thus, hyperconjugation explains why substituted alkenes are more stable than unsubstituted ones. Next important short question is 4. Define carbocation, Carbanian, and free radical. Carbocation, Carbanian, and free radical. In organic reactions, reaction intermediates are short-lived species. The most important ones are carbocation, Carbanian, and free radical. 1. Carbocation. A carbocation is a positively charged carbon species in which carbon has only 6 electrons. It is electron deficient and highly reactive. Example: CH, CH, C. Stability order 3 to 1. CH due to hyperconjugation. 2. Carbanian. A carbanian is a negatively charged carbon species with 8 electrons and a lone pair. It is electron-rich and acts as the nucleophile. Example: CH. Stability order CH 1, 2, 3, opposite to carbocation. 3. Free radical. A free radical is a neutral species containing one unpaired electron. It is very reactive and usually formed by homolytic bond cleavage. Example: CH. Easy memory tip. Cation. Anion. Radical 1. These intermediates help us understand reaction mechanisms and stability easily. Next important short question is 5. State Huckel's rule of aromaticity with examples. Huckel's rule of aromaticity. Huckel's rule is used to identify whether a compound is aromatic or not. According to this rule, a compound is aromatic if it satisfies all the following conditions. 1. The molecule must be cyclic, ring-shaped. 2. It must be planar, flat. 3. It must be fully conjugated, continuous overlap of p orbitals. 4. It must contain 4 n2 ELECTRNs, where n is a whole number, 0, 1, 2. Examples: Benzene, CH it has 6 ELECTRNs, N1412, so it is aromatic. Cyclopentadienyl anion, CH it has 6 ELECTRONs, hence aromatic. Non-aromatic anti-aromatic. Cyclobutadiene has 4 ELECTRONs, 4N, so it is anti-aromatic and unstable. Easy memory tip. Aromatic 4N2, think +2 stable. Thus, Huckel's rule helps us easily predict stability and special behavior of aromatic compounds. Next important short question is 6. Define ortho, meta and para-directing groups. Ortho, meta and para-directing groups. In electrophilic aromatic substitution reactions, like nitration or halogenation of benzene, the group already present on the benzene ring controls where the new group enters. Such groups are called directing groups. Ortho and para-directing groups. These groups direct the incoming group to the ortho 1, 2 and para 1, 4 positions of the benzene ring. They usually donate electrons to the ring by I or M effect. Examples: OH, NH, CH, OCH. Example reaction: toluene HNO O nitrotoluene P nitrotoluene. Meta-directing groups. These groups direct the incoming group to the meta 1, 3 position. They withdraw electrons by I or M effect, making ortho and para positions less reactive. Examples: NO, CN, Q, SOH. Easy memory tip. Donating ortho, para. Withdrawing meta. Thus, directing groups help predict product position in aromatic reactions easily and clearly. Next important short question is 7. Apply resonance effect to the acidity of phenol and basicity of aniline. Mention the directing effect of halo groups. Resonance effect, acidity of phenol, basicity of aniline and directing effect of halogens. Acidity of phenol. Phenol is more acidic than alcohol because of the resonance effect. When phenol loses a proton, H, it forms the phenoxide ion. The negative charge is delocalized over the oxygen and the benzene ring through resonance. This stabilizes the conjugate base, making phenol more acidic. Example: phenol ethanol, acidity. Basicity of aniline. Aniline is less basic than ammonia due to resonance. The lone pair on nitrogen is partially delocalized into the benzene ring by +M effect, so it is less available to accept a proton. Hence, aniline shows reduced basicity. Order: ammonia aniline. Directing effect of halo groups. Halogens Cl, Br, I show I effect, electron withdrawing. But +M effect, electron donating by resonance. Because of +M effect, halogens are ortho-para-directing, but due to I effect, they deactivate the benzene ring. Easy memory tip. Resonance stabilizes phenoxide more acidity. Resonance uses lone pair of N less basicity. Halogens, OP directing but deactivating. Next Unit 2. Long questions. First important long question is: explain inductive, resonance and hyperconjugation effects and apply them to A. Basicity of amines. B. Acidity of carboxylic acids. C. Stability of carbocations, carbanions and free radicals. Inductive, resonance and hyperconjugation effects and their applications. In organic chemistry, electronic effects explain why molecules show different reactivity, acidity, basicity and stability. The three most important effects are inductive effect, resonance effect and hyperconjugation. 1. Inductive effect, I effect. The inductive effect is a permanent effect caused by unequal sharing of electrons due to electronegativity difference. It works through sigma bonds and decreases with distance. I effect, electron withdrawing no Cl. Plus I effect, electron donating CH, alkyl groups. 2. Resonance effect, M effect. The resonance effect involves delocalization of pi electrons or lone pairs over a conjugated system. It increases stability by spreading charge. Plus M effect or NH. M effect no Cn. 3. Hyperconjugation. Hyperconjugation is the interaction of CH sigma electrons with an adjacent pi system or empty p orbital. It is also called no-bond resonance and stabilize molecules. Applications. A. Basicity of amines. Basicity depends on the availability of the lone pair on nitrogen. Plus I effect of alkyl groups increases electron density on N, so basicity increases. Order: gas phase 3 degrees greater than 2 degrees greater than 1 degree NH. In aniline, resonance delocalizes the lone pair into the benzene ring, making it less available, so aniline is less basic than ammonia. Memory tip: more electron density on N more basic. B. Acidity of carboxylic acids. Acidity depends on the stability of the conjugate base, carboxylate ion. I groups, Cl, no, pull electrons and stabilize the negative charge, increasing acidity. Example: ClCH2CH2. Resonance in the Cu ion spreads the negative charge over to oxygen atoms, making carboxylic acids stronger than alcohols. Memory tip: more stable conjugate base, stronger acid. C. Stability of reaction intermediates. Carbocations. Stabilized by plus I effect and hyperconjugation. Order 3 degrees greater than 2 degrees greater than 1 degree Ch. Carbanions. Stabilized by I effect and resonance. Order Ch greater than 1 degree 2 degrees greater than 3 degrees. Free radicals. Stabilized mainly by hyperconjugation. Order 3 degrees greater than 2 degrees greater than 1 degree Ch point. Final memory line. Carbocation and radical like electron donation. Carbanion likes electron withdrawal. Conclusion. Inductive, resonance and hyperconjugation effects together explain basicity, acidity and stability, making organic reactions logical and easy to remember for exams. Next important long question is: 2. Discuss the preparation and chemical reactivity of alkanes, including preparation from Grignard reagents and free radical halogenation mechanism. Preparation and chemical reactivity of alkanes. Alkanes are saturated hydrocarbons containing only single, sigma, bonds with the general formula CH. They are also called paraffins, meaning little reactivity, but they do show important reactions under suitable conditions. Preparation of alkanes. 1. From Grignard reagents. Grignard reagents have the formula RMGX, R is equal to alkyl group, X is equal to halogen. When a Grignard reagent reacts with water, alcohol or dilute acid, it gives the corresponding alkane. Reaction: RMGX plus HORH plus Mg, or X. Example: CHMgBr plus HOCH plus Mg, or Br. This method is useful for preparing alkanes with one more carbon atom from alkyl halides. Memory tip: Grignard plus water is equal to alkane. 2 other methods, brief. Wurtz reaction, alkyl halides plus Na higher alkane. Kolbe's electrolysis, from sodium salts of acids. Chemical reactivity of alkanes. Alkanes are generally less reactive due to strong C, C and CH bonds. The most important reaction is free radical halogenation. Free radical halogenation mechanism. When alkanes react with halogens, Cl or Br, in the presence of sunlight or heat, substitution occurs. Example: chlorination of methane. CH plus Cl CHCl plus HCl. This reaction occurs in 3 steps. 1. Initiation. Cl to Cl point by UV light. Free radicals are formed. 2. Propagation. Cl point plus CH point plus HCl. CH point plus CH plus Cl point. The chain reaction continues. 3. Termination. Cl point plus Cl point Cl. CH point plus Cl point CHCl. Free radicals combine and the reaction stops. Memory tip: Initiation, propagation, termination, IPT. Reactivity trend. Chlorination is fast but less selective. Bromination is slower but more selective. Conclusion. Alkanes can be prepared easily from Grignard reagents and show reactions mainly through free radical mechanisms. Understanding these reactions helps in mastering reaction mechanisms for exams. Next important long question is: 3. Explain the preparation of alkenes by A. Dehydration of alcohols. B. Dehydrohalogenation of alkyl halides. C. Dehalogenation of vicinal dihalides. And discuss Zaitsev's rule. Preparation of alkenes and Zaitsev's rule. Alkenes are unsaturated hydrocarbons containing at least one C is equal to C double bond with the general formula CH. They are important intermediates in organic chemistry and industry. Alkenes are commonly prepared by elimination reactions, where small molecules are removed. A. Dehydration of alcohols. Dehydration means removal of water, HO, from alcohols. This reaction is carried out by heating alcohols with concentrated HSO or ALO. Reaction: RCH or RCH is equal to CH plus HO. Example: ethanol ethene plus water at 170 degrees Celsius, conc. HSO. Mechanism: 2 degrees and 3 degrees alcohols follow E1 mechanism via carbocation. 1 degree alcohols follow E2 mechanism. Memory tip: alcohol HO is equal to alkene. B. Dehydrohalogenation of alkyl halides. Dehydrohalogenation means removal of HX, HCl, HBr from alkyl halides. This is done by heating alkyl halides with alcoholic KOH. Reaction: RCH X plus KOH RCH is equal to CH plus KX plus HO. Example: bromoethane plus AlC. KOH ethene. This reaction occurs by E2 mechanism. Memory tip: alkyl halide plus AlC. KOH is equal to alkene. C. Dehalogenation of vicinal dihalides. Vicinal dihalides have two halogen atoms on adjacent carbon atoms. When treated with zinc dust, the two halogen atoms are removed, forming an alkene. Reaction: RCHX CHX R plus Zn RCH is equal to CH R plus Znx. Example: 1,2-dibromothane plus Zn ethene. Memory tip: vicinal dihalide X is equal to alkene. Zaitsev's rule. According to Zaitsev's rule, during elimination reactions, the more substituted alkene with more alkyl groups attached to the double bond is formed as the major product because it is more stable due to hyperconjugation. Example: 2-bromobutane mainly but 2-Na, not but 1-Na. Final memory line: rich get richer, more substituted alkene dominates. Conclusion: alkenes are prepared by dehydration, dehydrohalogenation and dehalogenation, and Zaitsev's rule helps predict the major product easily in exams. Next important long question is: 4. Discuss the addition reactions of alkenes with suitable mechanisms: halogenation, anti-addition, addition of HX, Markovnikov and anti-Markovnikov, hydration, Hox addition, hydroxylation, epoxidation and ozonolysis. Addition reactions of alkenes with simple mechanisms. Alkenes contain AC is equal to C double bond, which is rich in electrons. Because of this, alkenes mainly undergo addition reactions, where atoms add across the double bond. Important reactions are explained below in simple words. 1. Halogenation, anti-addition. When alkenes react with Cl or Br, in CCl, halogens add across the double bond. Example: ethene plus Br1, 2-dibromothane. Mechanism: a bromonium ion is formed first, and then Br attacks from the opposite side, giving anti-addition. Memory tip: halogenation is equal to anti-addition. 2. Addition of HX, HCl, HBr, high. A. Markovnikov's rule. Hydrogen attaches to the carbon having more hydrogen atoms, and X attaches to the other carbon. Example: propene plus HBr to bromopropane, major. B. Anti-Markovnikov, peroxide effect. In the presence of peroxides, HBr adds in the opposite way by a free radical mechanism. Memory tip: peroxide plus HBr anti-Markovnikov. 3. Hydration of alkenes. Alkenes react with water in the presence of acid, HSO, to form alcohols. Example: ethene plus HO ethanol. Follows Markovnikov's rule. 4. Hox addition, halohydrin formation. When alkenes react with ClBr in water, Hox adds across the double bond. Example: ethene plus Br plus HO bromohydrin. Or goes to the more substituted carbon. Memory tip: Hox off on richer carbon. 5. Hydroxylation. Alkenes react with cold dilute alkaline KMNO to form vicinal diols, glycols. Example: ethene ethane 1,2 diol. This is a SYN addition. 6. Epoxidation. Alkenes react with peracids, RCOH, to form epoxides, three-membered oxygen ring. Example: ethene ethylene oxide. Memory tip: peracid epoxide ring. 7. Ozonolysis. Alkenes react with ozone, O, followed by ZnHO to break the double bond and form aldehydes or ketones. Example: ethene to molecules of formaldehyde. Memory tip: ozonolysis is equal to cut the double bond. Conclusion: alkene reactions follow clear rules like Markovnikov, anti-addition and SYN addition. Remembering the type of reagent makes these reactions easy and scoring in exams. Next important long question is 5. Explain the preparation, properties, and chemical reactions of alkynes, including electrophilic addition, hydration with tautomerism, oxidation and reduction. Preparation, properties, and chemical reactions of alkynes. Alkynes are unsaturated hydrocarbons containing at least one carbon-carbon triple bond, CC. General formula CH. Example: ethylene, CH. Preparation of alkynes. 1. From vicinal dihalides, double dehydrohalogenation. When vicinal dihalides are heated with alcoholic KOH, two molecules of HX are removed, forming alkynes. Example: CHBr plus to KOH HCCH plus to KBr plus to HO. 2. From calcium carbide. Calcium carbide reacts with water to give acetylene. CaC plus to HOCH plus CaO. Properties of alkynes. Alkynes are nonpolar and insoluble in water. They undergo addition reactions easily due to the triple bond. Terminal alkynes show weak acidic nature due to sp hybrid carbon. Chemical reactions of alkynes. 1. Electrophilic addition. Alkynes react with halogens, Cl, Br, or HX. Example: HCCH plus Br BrCH is equal to CHBr, dibromolkene. 2. Hydration with tautomerism. In presence of HgSO and dilute HSO, water adds to alkyne forming enol, which changes into ketone, tautomerism. Example: HCCHCH is equal to CHO, enol, CHCHO, aldehyde. Remember, enol is unstable changes to keto form. 3. Oxidation. Strong oxidizing agents like KMNO or O break the triple bond forming acids or ketones. Example: HCCH plus O. CO plus HO. 4. Reduction. Alkynes can be reduced to alkenes or alkanes. Lindlar's catalyst C-isalkene. Na-NH transalkene. Ni-PT alkane. Easy memory tip. Alkynes love addition, show tautomerism, break in oxidation and change form in reduction. Next important long question is 6. Discuss aromaticity with reference to Huckel's rule and explain the general mechanism of electrophilic aromatic substitution. Aromaticity and electrophilic aromatic substitution EAS. Aromaticity and Huckel's rule. Aromaticity is a special stability shown by some cyclic organic compounds due to delocalized pi electrons. A compound is aromatic if it satisfies Huckel's rule, which states that a molecule must have 4n plus 2 pi electrons, where n is equal to 0, 1, 2. Conditions for aromaticity. 1. Cyclic, ring-shaped. 2. Planar, flat. 3. Fully conjugated, continuous p-orbital overlap. 4. 4n plus 2 pi electrons. Example. Benzene, CH, has 6 pi electrons, n is equal to 1, so it is aromatic and highly stable. Other examples include naphthalene, 10 pi electrons, and cyclopentadienyl anion, 6 pi electrons. Memory tip. Aromatic is equal to circle plus flat plus conjugated plus 4n plus 2. Electrophilic aromatic substitution, EAS, general mechanism. Aromatic compounds prefer substitution reactions rather than addition because addition would destroy aromatic stability. The most common reaction is electrophilic aromatic substitution, EAS. General steps of EAS. 1. Generation of electrophile. A strong electrophile, E, is generated using a catalyst. Example. Nitration, NO from HNO plus HSO. Halogenation, Cl from Cl plus FeCl. 2. Formation of sigma complex, arenium ion. The electrophile attacks the benzene ring, forming a sigma complex, also called arenium ion. In this step, aromaticity is temporarily lost, and the intermediate is stabilized by resonance. This is the slow, rate-determining step. 3. Deprotonation and restoration of aromaticity. A proton, H, is removed, and the aromatic ring is restored. Example, nitration of benzene. CH plus HNO CHNO plus HO. Why EAS is favored? Aromatic rings are very stable. Substitution preserves aromaticity. Easy memory line. Make electrophile break aromaticity, restore aromaticity. Conclusion. Huckel's rule explains why aromatic compounds are stable, and the EAS mechanism explains how they react without losing stability. These concepts are core ideas in organic chemistry and exams. Next important long question is 7. Explain orientation and reactivity in electrophilic aromatic substitution reactions, including nitration, sulfonation, halogenation, Friedel-Crafts alkylation and acylation, and the role of activating and deactivating groups. Orientation and reactivity in electrophilic aromatic substitution, EAS. In electrophilic aromatic substitution, EAS, reactions, two important questions arise. 1. Where will the new group enter the benzene ring? Orientation. 2. How fast will the reaction occur? Reactivity. Both depend mainly on the substituent already present on the benzene ring. Activating and deactivating groups. Substituents affect electron density in the ring through inductive, plus II, and resonance, plus RR, effects. 1. Activating groups. These groups donate electrons to the ring and increase reactivity. They are usually ortho-para-directing. Examples of NH, OCH, CH. Why? They push electrons into the ring, making ortho and para positions richer in electrons. Example. Toluene, CH group, undergoes nitration faster than benzene and mainly gives ortho and para-nitrotoluene. 2. Deactivating groups. These groups withdraw electrons from the ring and decrease reactivity. Most are meta-directing. Examples: No, Ku, Soh, Cho. Why? They pull electrons away, making ortho and para positions less stable. Example: nitrobenzene undergoes nitration slowly and mainly gives metadinitrobenzene. Special case: halogens. Halogens Cl, Br are deactivating but ortho, para directing. I effect reduces reactivity. Plus R effect directs to ortho and para positions. Example: chlorobenzene gives ortho and parachloronitrobenzene, but reaction is slow. Orientation in important EAS reactions. 1. Nitration, no introduction. Reagent HNO plus HSO. Activating groups ortho para. Deactivating groups meta. 2. Sulfonation, SOH introduction. Reagent fuming HSO. Reversible reaction. Orientation follows the same directing rules. 3. Halogenation, Cl, Br. Reagent Cl Fe Cl or Br Fe Br. Halogens direct ortho para but slow the reaction. 4. Friedel-Crafts alkylation. Reagent R Cl plus UlCl. Works well with activating groups. Fails with strong deactivating groups like NO. 5. Friedel-Crafts acylation. Reagent RCOCl plus UlCl. Gives ketones. No rearrangement and more controlled than alkylation. Easy memory trick. Electron donating is equal to fast plus ortho para. Electron withdrawing is equal to slow plus meta. Halogens is equal to slow but ortho para. Conclusion. Orientation and reactivity in EAS are controlled by substituents on the benzene ring. Understanding activating, deactivating, and directing effects makes EAS reactions easy to predict and remember for exams.